Welcome back to Physical Science 20. This is the first part in PW2 looking at wave reflection. So similarly to what we did before, we'll look at ropes and springs, and then move on to water waves, and then sound waves, and then finally light waves. So looking at waves at a boundary. So recall from earlier, the speed of a wave depends on only the properties of the medium that it passes through and not the wave's amplitude or frequency. So it depends on characteristics of the medium itself. If we're looking at water waves, we're looking at the depth of water, which affects the wave's speed, whether it's deep or shallow. For sound waves, through air, it's the air temperature that affects the speed. If we're looking at springs or ropes, it depends upon the tension or mass per unit length. So those are key points to underline there, folks. Examine what happens when a wave travels across a boundary from one medium to another, such as two springs of different thicknesses joined end to end. Figure 13 shows a wave pulse traveling from a larger spring to a smaller one. Okay, the pulse that strikes a boundary is called the incident wave. One pulse from the larger spring continues in the smaller spring, but the speed of the pulse is different in the smaller spring. Note that this transmitted wave pulse remains upward. So if we look here, and we'll be doing a lot of these demos in our classroom. So here you have a heavier spring and a lighter spring, and you can see that before and after. So there is a reflection on the same side as the spring and a transmission on the opposite side of this spring, and this could be higher or lower. We'll take a look in the classroom and see exactly how that works. Some of the energy of the incidence wave's pulse is reflected backwards into the larger spring. The returning wave is called a reflected wave, so it goes backwards upon itself. Whether the reflected wave is upright or inverted depends upon the characteristic of the two springs. For example, if the waves in the smaller spring have a greater speed, because the spring is stiffer, then the reflected wave will be inverted. Okay, so we'll take a look at that. If this had been a stiffer spring, this likely would have been inverted upside down. If you look at rigid boundaries in which we can't transfer energy, when a wave pulse hits a rigid boundary, the energy is reflected backwards. The wall is the boundary of the new medium through which the wave attempts to pass. Instead of passing through, the pulse is reflected from the wall with almost exactly the same amplitude that it had with the incident wave. Thus, almost all of the wave's energy is reflected back. Very little energy is transmitted to the wall. Also note, if it hits a rigid boundary as opposed to a movable boundary, it is inverted. So if it was on the top, it'll be on the bottom with this one. Okay, so that's just a little bit on wave reflection. In the classroom, we'll look at some demos and look at specific springs and incidences and see exactly what happens. On the side with this is the formation of standing waves, which we'll also do in class. So continuously setting pulses in motion, and they interfere with the reflected pulses, you get patterns that look like this. So if you at specific frequencies, we get what is referred to as standing waves. So they look like they're standing still, even though they're continuously transmitting and reflecting and interfering pulses. So the ends of the rope are nodes. We talked about this earlier, the areas of cancellation. There's an area of cancellation, so node, 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 node. And in between the nodes is an area in which they interfere constructively. So here's node, antinode, 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 antinode. So node are areas of destructive interference, as we talked about earlier. Antinodes are areas of constructive interference, making a wave that's bigger than previously. Just an aside here too, so in this picture, if we were figuring how many wavelengths we see, so in this one, looking at corresponding pieces, we're halfway, because if I kept going, I'd meet my corresponding parts. That's half a wavelength. This diagram, if we see two sets of antinodes, oh, and I've reached the corresponding point that I had over here. That is one full wavelength. One full wavelength plus a half. So half wavelength, one wavelength, and 1.5 wavelengths. When waves reflect and interfere with each other in a standing wave pattern. All right. One final thing, looking at waterways. We'll look at that on the next video. So with this current one, slinkies, ropes, in class we'll take a look at some more scenarios here, and we'll also look at the standing wave pattern as well. All right? There's also an assignment that goes along with this, and we'll see you again.